All right, let's make sure I'm recording. Yep. All right, good. All right, so this will be actually kind of a quick review. This is really just an algebra topic, but it's one that, I mean, people remember once you actually remind them, but it's something that comes up a lot in calc, especially when you're trying to find areas between regions and that sort of thing, and other applications. And so I just wanted to make sure that everyone had a quick recall of what solving linear systems looked like, just the basic methods. Okay, so we know how to solve one equation if it involves one variable, and we know how to graph a single linear equation if it involves two. But the question now becomes, what if you have two linear equations, both of which have to hold at the same time, right? So they hold what's said to be simultaneously. So a solution to a system like that would be a point involving having an x and a y coordinate that satisfies both equations of the system. So for instance here, if you put 5 in for x and 3 in for y, you'll notice that both of these equations are satisfied. And so we'll call 5, 3 a solution of the system. But if you clunked in 4 for x and 2 for y, it satisfies the first equation, but not the second. And so it's not a solution of the system, right? You have to satisfy both equations of the system in order for it to be a solution. Now the question is, I don't want to have to sit here and guess as to what the x and the y would be. There might not even be one for that matter. So how do you solve it? And what you do, there are two basic methods. One's called substitution, and the other you know of as elimination, right? So just a quick recall of what substitution is. You have two equations in x and y. What you want to do is solve one of those equations for a variable, right? So you have a choice. And what I did in this particular example is I solved the first equation for y. I chose that because I wouldn't have to divide by a coefficient, right? So I'm trying to avoid fractions if I can, if it's even possible. And I could do that if, in fact, I solved this for y. You could alternatively have solved this guy for x, right? Either one will yield the end solution to be the same, right? So it's your choice. But the minute you do that, like I did here, then you plug this in for that variable in the equation that you did not touch in the first place. So here, since I solved the first guy for y, I'm going to plug this in for y in the second equation. All right, and so I literally substituted in. Notice that what you get is a linear equation involving only x, and so you solve this like you normally would any linear equation to find what the x value is, namely x equals 2. And then you plug that x equal to 2 back into the equation you got from your substitution, right? So if I plug it back here, you get 3 minus 4, which is -1. So the y coordinate happens to be -1. And hence the solution is 2, -1, right? That's basically the idea of substitution. All right. So I'll let you do that. I'm not going to spend a lot of time on this because I figured you can do it. So go ahead and try this your turn and then check yourself to make sure that you're on the right track with it. For elimination, there are two, basically here the idea is you multiply one or both equations by the right constant so that when you add the two equations down, meaning you add the lefts and you add the rights, one of the variables drops out, right? That's the general notion here. And so the easiest case, of course, is when the equations involve the same variable but with the opposite coefficient. So plus and a minus. So here I have a -y and a positive y. So if I literally just add the lefts and add the rights like I do here, I eliminate the variable y. So I only get an x term on this side and a constant on that side, right? So right there, I'll get that x is 10. And then the way you find the y coordinate is by simply plugging x equal to 10 back into either of these equations. It does not matter which one. And then you'll find y is 32. All right. For this one, it's a little bit worse because I can't just add the lefts and add the rights. If I do that, one of the variables does not drop out, right? And so what you first have to do is multiply both sides, let's say, of this equation by just the right number so that when you do add them, a variable drops out. And that number that I'm going to multiply this by is, of course, 3, because I want the 3x and then the negative 3x to drop out. And so that's what I do here, right? I'm multiplying both sides by 3, right? And so you can, if you line up the terms, you'll see the 3x's go, and I get 11y equals negative 11, right? Solve that for y, and then plug that y value back into either of these equations, doesn't matter, to find the x value. The worst case is when you have all different coefficients, right? So that's the case in your turn 2, where here you wouldn't want to use substitution even if you were allowed to, because you're going to get fractions, right? Will it work? Yes. Do you want to do it with fractions? Probably not. Right? It's just more of a nightmare than is anything else, right? So, and here for elimination, I can't just multiply one equation by something unless I want to use fractions, which I don't, right? And so what you'll have to do is choose to multiply both equations by just the right numbers so that when you add them, a variable drops out, right? And so let's just look at the solution. If I multiply the first equation by 3 and the second one by -2, like I suggest here, the x terms when you add them will actually cancel out. Just make certain that you multiply every term in the equation on both sides by the number that you choose in each case, right? Don't just multiply the term you're trying to kill off by it, right? Then it'll throw off the whole system. Once you've done that, the hard work is done, right? You add them down, the x terms go, and then you can just solve this equation for y, and then plug it back into either of those to find what the x value is, right? So the hard work, so to speak, is in trying to multiply both these guys by just the right number to make it work out. All right, 2 special cases, right? So those cases, notice we only got a particular value of x and y that worked, and so you could visualize that as 2 lines that intersect in a point, right? So kind of like this. But 2 lines could be parallel. If they're parallel, they don't intersect. And so there should not be a solution to a system in which the lines are parallel. Right? And so that's the case here. Notice here, if you were to solve each of these for y, right? So I move the x term over here to get y equals x plus 3. Here, if I shuffle these terms, I get y equals x plus 1. Both of those lines, if you were to try to graph them, have a slope of 1, and the y-intercepts are different, right? And so you have one of them going through +1 on the y-axis and one of them going through +3, but they have the same slope. And so they're parallel, so they don't intersect. What will happen algebraically, if that's to actually happen, is that no matter what method you get or what method you use, if it's substitution or elimination, what's going to happen is you'll get a false statement, right? As long as you're careful, you'll get a statement like here where 0 is equal to 2. We know that that can't happen. And so apparently the method itself yields a false statement, which means there is no solution. The other case that can happen is that these 2 lines are actually the same, but in disguise, right? So that often happens when one's a multiple of the other, okay? And that's what happens here. So here, notice if I were to multiply both sides of the first equation by 2, I get exactly the second one, right? And so if you try to use elimination to solve this, if I multiply by -2, like I did here on both sides, and you add, everything drops out and you get 0 equal to 0. What that means is that it wouldn't have mattered what values of x and y on this line you chose, it would automatically be on this line. And so every point on this line is actually a solution, right? The lines are exactly on top of each other or coincident. They happen to be the same line. All right, so I'll let you go through these solutions or these systems here. Just do it carefully. You could use either substitution or elimination, right? Whichever, try to figure out which one makes the most sense to use. Like here, there's something that is crying out to be used, whereas here something else might be wanted to be used. Okay, so just try to pick out the most efficient method so that you can minimize your work. And then we'll check that. Just so pause the video and then do those, and we'll check your solutions here in a moment. All right, so for the first one, it cries out to be, well, you could actually, let's see. Well, okay, it cries out to, what I was thinking before I looked at my solution is that I would have tried substitution, because one of them is already solved for y. If you did that and you plugged it up here, you would have gotten 10 minus 2x on the left and 10 minus 2x on the right, which is always true no matter what x you give me, right? And so another way of saying that is if I were to rewrite this equation by dividing both sides by 2, I'll get the exact same equation. So I'm removing that multiple of the first equation, kind of removing its disguise, if you will. And so I can see that you get exactly the same equation back. And so there are infinitely many solutions here, namely any point on this line would be a solution. Let's skip down to number 3. Number 3 cries out for elimination because you have the same but opposite coefficient on one of the variables, right? So if you just add the left and add the right, the x's drop out. I get 2y equal to 14, so I know what the y value is, and then plug that y value back in to find the x, right? So you only have a unique solution to that one, namely this point. This one here, you wouldn't necessarily know to actually rewrite the equations in this way, right? I'm doing it to illustrate a point. Naturally here you might have, you would have taken one term over to the left and tried elimination, right? If you were to try elimination, what you would get is a false statement in the end, right? So notice if I were to subtract both sides here, everything on the left would drop out. I'd get 3 minus a negative 1, which is 4. So I would get the equation 0 equals 4, which obviously is false, right? And so this system, you have 2 equations that have the same slope, namely 2/3, but different y-intercepts. And so they're parallel, hence there's no solution. All right, so go ahead and give these a go. Most of them are, basically the same idea. Some little subtleties involving fractions and decimals. And sometimes here you have to do a little bit of simplification before you can actually leap in to using one of the techniques. That's the only subtlety that will be there. So go give them a go and let me know how that goes.